Physics. Concerning the subject matter of physics, one thing seems to be traditionally taken for granted. The object of its study is the sensible world of changing things or matter in motion. When Plato, for example, conceives astronomy as dealing not with the actual and observable motions of the heavenly bodies, but with the possible forms of the motions of solids. He gives it the character of a mathematical rather than a physical science. He associates it with geometry, as for a similar reason he associates music, divorced from concern with audible harmonies, with arithmetic. In anyone's view, if a science does not investigate sensible realities, if it does not undertake to account for the motions of actual bodies, or, stated most generally, if it has no concern with the phenomena of change, then it does not have the character of physical or natural science. The early Greek physicists, the pre-Socrates, to whom Plato and Aristotle refer, inaugurate the study of change with speculations about ultimate origins, the underlying principles or causes of natural phenomena. Sometimes they are called philosophers and sometimes scientists, or at least precursors of empirical science. But there seems to be no difference of opinion about their title as physicists. Their undisputed claim to this title derives not from the method they employ, but from the object they study: change. In that primary meaning of the word, nature, which comes from the Latin natura, the equivalent of physis in Greek, they can be called naturalists or physicists indifferently. The realm of nature is the realm of change. It is for this reason that Aristotle, considering the theories of his predecessors in the opening chapters of his Physics, sets Parmenides apart from all the rest. Parmenides' affirmation of the unity of being, which leads to his denial of the reality of change or motion, cannot be treated as a physical theory. On the contrary, it is, according to Aristotle, a complete negation of the subject matter of physics. No matter what other points physicists may dispute among themselves, they must all at least agree in taking a stand against Parmenides. Aristotle does not even seem to think that a book on physics is the proper place to argue against Parmenides. That argument belongs to another part of philosophy. The reality of change seems to him sufficiently evident to assure the physicist that he has a subject matter to investigate. The question whether the early physicists or scientists or philosophers, calls attention to different methods of investigating natural phenomena. Agreement on the subject matter of physics may prevail, therefore, only in very general terms, when in a manner to accord with the method employed, the object of physical inquiry is more specifically defined. There seem to be two physics, not one, a philosophical and a scientific physics, a philosophy of nature and a natural science, or to use Kant's phrasing, a traditional or pure physics and an empirical or experimental physics. Though Newton may call his work a philosophy of nature, he also refers to it as an experimental philosophy in order to distinguish it from the work of earlier natural philosophers who did not perform experiments. The difference between the physics of Newton and that of Aristotle seems, however, to involve more than a divergence in method. The problems which Newton and Aristotle try to solve indicate a difference in subject matter as well. Nevertheless, this difference falls within what, in the most general terms, must be conceived as the domain of physics. For all their differences, both are physicists, though both are not philosophers or scientists in the same sense. There are other sources of variation in the definition of physics. The problem of the relation of physics to other disciplines, whether these are other branches of philosophy or other fields of empirical research, raises issues about the object and scope of physics. Aristotle, Bacon, Descartes, and Kant, for example, do not seem to have a common understanding of the relation of physics to mathematics and metaphysics. In consequence, they conceive physics itself differently. On the level of empirical research, physics is sometimes regarded as just one of the natural sciences, and sometimes as the whole group of natural sciences. In the latter case, it includes such fields as astronomy, mechanics, optics, acoustics, thermodynamics, magnetism, and electricity. And sometimes chemistry, biology, and even psychology are included under the head of physical or natural sciences, contrasted in the broadest terms to the social sciences. The conception of physics obviously changes when its scope is determined by a boundary line which separates it from chemistry, or from biology and psychology, or from the study of society. The separation of these other sciences from physics does not necessarily imply a discontinuity in nature or the natural sciences. The biologist and the psychologist, for example, consider the physical basis of life and the physical conditions or correlations of mental phenomena. Hybrid sciences like biophysics and psychophysics have developed. Even the study of society draws upon physics to the extent that the laws of matter in motion and considerations of space and time must be appealed to for an understanding of the physical foundations of economic and political life. Other chapters deal with specific physical sciences, e.g., astronomy and mechanics. The latter tries to cover the various branches of mechanics and related fields of study, such as dynamics, optics, theory of heat, magnetism, and electricity, particularly so far as these are represented in the work of Galileo, Newton, Huygens, Gilbert, Fourier, and Faraday. The basic concepts of mechanics and its branches or affiliates are also treated in that chapter. Still, other chapters deal with fundamental terms representing concepts or problems in the larger domain of physics. Philosophical or scientific, e.g., cause, change, element, infinity, matter, principle, quantity, space, and time, not to mention nature and world, terms which represent in the most comprehensive way the reality studied by the physicist. Our discussion here can therefore be restricted to the problems raised in the great books concerning the conception of physics, its subject matter and method, its relation to other sciences or other parts of philosophy. It will lead to such questions as whether physics is supreme among the sciences, studying reality or the nature of things, and at the other extreme, whether there can be scientific knowledge of bodies in motion, or of the whole realm of change and becoming. The problem of the distinction between philosophical and scientific physics would appear to be only a special case of the distinction between philosophy and science in general. But it is more than that. It is the case which tests the main distinction itself, since here both philosopher and scientist claim to be expounding the same subject matter, or at least to be dealing with the same general field of phenomena. Mathematics and metaphysics bear on the distinction between philosophy and science in a different way. If, for example, we take experimentation or empirical research to be characteristic of science in distinction from philosophy, then mathematics would seem to resemble philosophy rather than science. On no understanding of the nature of mathematical knowledge is mathematics ever divided into two kinds which are capable of being described as empirical and rational. The possibility of metaphysical knowledge may be challenged, but no one has ever proposed an experimental metaphysics to challenge the metaphysics of the philosophers. But physics seems to permit both an experimental and a philosophical treatment, whether they are to be regarded as in conflict with one another depends on whether they are attacking the same problems by different methods, or whether they represent something like a division of labor. In the latter view, each would deal according to its method with different problems and tend to supplement rather than to exclude the other. Psychology is another subject matter which seems to receive a dual treatment, philosophical and experimental. In the tradition of the great books, it raises issues similar to those just mentioned. They are considered in the chapter on man. As the chapters on philosophy and on science indicate, the discussion of their differences from and relation to one another is complicated by the double use of both terms. The word science, for example, is used for both the philosophical and the experimental sciences throughout the greater part of the tradition. Similarly, until quite recently, the name of philosopher is taken by those who experiment as well as by those who do not. It is impossible, therefore, to speak without confusion of a scientific and a philosophical physics unless the verbal ambiguities are resolved by some convention, such as the understanding that when the context indicates that the words science and philosophy are being used as opposites rather than as synonyms, then science shall signify the experimental and philosophy the non-experimental mode of treatment. Beyond this, it is necessary to proceed as if the chapters on philosophy and science formed a background for some of the matters to be discussed here. Otherwise, the consideration of natural philosophy and natural science would tend to become a general discussion of philosophy and science. The great books of experimental physics seem to have three characteristics in common. First, and most naturally, they insist upon experimentation as either the indispensable source of or the ultimate test of scientific formulations. Second, they tend to rely upon mathematics as much as upon experiment, both for the formulation of nature's laws and for the demonstration of the consequences or corollaries of the primary laws. Third, though experiments and observations multiply as science develops, they seek to bring all the phenomena of nature under the smallest number of generalizations which have the utmost simplicity in mathematical statement. On the second and third points, Newton's declarations seem to be most explicit. Nature, he says, is pleased with simplicity and affects not the pomp or superfluous causes. Accordingly, Newton directs his efforts toward the simplest statement of the laws of motion, and these he seeks to give the universality requisite for covering every type of natural phenomenon. At the beginning of the third book of the Mathematical Principles of Natural Philosophy, he explains that in the preceding books he has laid down the principles of philosophy, principles not philosophical but mathematical, such namely as we may build our reasonings upon in philosophical inquiries. These principles are the laws and conditions of certain motions and powers or forces. From these same principles he will now undertake to demonstrate the frame of the system of the world. In the preface to the first edition of this work, Newton describes the third book as one in which he derives from the celestial phenomena the forces of gravity, with which bodies tend to the sun and the several planets. Then from these forces, by other propositions, which are also mathematical, he goes on, I deduce the motions of the planets, the concepts, the comets, the moon, the sea. But he does not consider his work to have attained the goal of physics, the comprehension of all natural phenomena by a few simple mathematical formulae. His confession of failure may also be as a prognostication of what an experimental physics based on mathematical principles might someday be able to achieve. I wish we could derive the rest of the phenomena of nature by the same kind of reasoning, he writes, for I am induced by many reasons to suspect that they may all depend upon certain forces by which the particles of bodies, by some causes hitherto unknown, are either mutually impelled towards one another and cohere in regular figures, or are repelled and recede from one another. Einstein's unified field questions cover both gravitational phenomena on the astronomical scale and the electrical attractions and repulsions of subatomic particles, covering both the gravitational phenomena on the astronomical scale and the electrical attractions and repulsions of subatomic particles, seem to realize, or at least closely to approximate, the ideal Newton has in mind. Midway between Newton and Einstein, Fourier also bears testimony to the ideal of physics as a science at once simple in its principles and universal in the scope of their application. The successors of Newton and Galileo, he writes, have extended their theories and given them an admirable perfection. They have taught us that the most diverse phenomena are subject to a small number of universal laws which are reproduced in all the acts of nature. It is recognized that the same principles regulate all the movements of the stars, their forms, the inequalities of their courses, the equilibrium and the oscillations of the seas, the harmonic vibrations of air and sonorous bodies, the transmission of light, capillary actions, the undulations of fluids, in fine, the most complex effects of all natural forces. Thus has the thought of Newton been confirmed. He concludes, referring to Newton's praise of geometry, whose glory it is that the few mathematical principles it provided for use in physics should have been able to produce so many things. On the experimental side, the great works of physical science seem to contain diverse notions of the purposes served by experimentation, accompanied by a fairly uniform recognition of the dependence of natural science upon experiment. In the field of magnetism, for example, Gilbert sets aside as unscientific all those authors who have written about amber and jet as attracting chaff, but with never a proof from experiments. These writers deal only in words. Such philosophy bears no fruit. The fruitfulness of experiments on the vacuum, the equilibrium of fluids, and the weight of air leads Pascal to conclude that the secrets of nature remain hidden until the experiments which supply us with knowledge about it can be performed and multiplied. We ought never to search for truth, but by the natural road of experiment and observation, writes Lavoisier, and Faraday describes himself as an experimentalist who feels bound to let experiment guide me into any train of thought which it may justify. The science of electricity, he finds, is in that state in which every part of it requires experimental investigation, not merely for the discovery of new effects, but ultimately for the more accurate determination of the first principles of action, of the most extraordinary and universal power in nature. Methods of experimentation necessarily differ in different fields. Of physical research, Newton's optical experiments with mirrors and prisms were adapted to the phenomena of light, as Galileo's experiment with the inclined plane, Pascal's experiment on the equilibrium of fluids, or Faraday's experiments with induction coils, were adapted to the phenomena of dynamics, hydrostatics, and electricity. The materials employed, the apparatus or instruments devised, the factors controlled or isolated from irrelevant circumstances, and the units of measurement in which the results are recorded naturally vary with the phenomena under observation. Yet one thing is common to the variety of experiments described in the great books of physical science. They all involve the construction of an artificial physical system which permits more accurate and refined observation than does nature uncontrolled or untampered with. The student of nature must observe in any case, no matter whether he is a philosopher or scientist. To say that philosophical physics is non-experimental does not mean for Aristotle that knowledge of nature is possible without observation or induction from experience. But the experimentalists insist upon the distinction between the kind of observations which men normally make in the course of everyday experience and the kind which involve the special experience enjoyed only by those who observe and, in addition, measure the results of specially contrived experiments. This point of distinction seems to be strikingly illustrated by a passage in Galileo's Two New Sciences. One of the persons in the dialogue, Simplicio, declares everyday experience to show the propagation of light to be instantaneous. He explains that when we see a piece of artillery fired at a great distance, the flash reaches our eyes without lapse of time, but the sound reaches the ear only after a noticeable interval. Sagredo replies that this familiar bit of experience permits him to infer only that sound, in reaching our ear, travels more slowly than light. It does not inform us, he says, whether the coming of light is instantaneous, or whether, although extremely rapid, it still occupies time. The choice between these alternatives could not be determined by ordinary experience. An experiment had to be constructed in order to measure the velocity of light. recourse to experimentation to find by observation and measurement the answers which ordinary experience fails to yield does not exhaust the use of experiment. The great experimental physicists indicate at least 3 distinct uses to which experiments can be put, in addition to a merely exploratory use for the discovery of new effects. In natural philosophy, as in mathematics, writes Newton, the method of analysis ought ever to precede the method of composition, or synthesis. In physics, the method of analysis consists in making experiments and observations and in drawing conclusions from them by induction. In contrast, the synthetic method begins with the principles assumed, therefore explaining the phenomena and proving the explanations. Here, experiments perform a probative rather than an inductive function. As Huygens observes, proof in physics does not have the certitude of mathematical demonstration, but it can have an extremely high degree of probability. Very often, scarcely less than complete proof, as a result of the experimental confirmation of a conclusion deduced from the assumed principles. This occurs when things which have been demonstrated by the principles that have been assumed correspond perfectly to the phenomena which experiment has brought under observation, especially when there are a great number of them. A single crucial experiment, so perfect in construction that all relevant factors have been controlled, makes unnecessary the multiplication of experiments to establish the conclusion. A third use of experiment is illustrated by Galileo when he measures the velocity of a ball rolling down an inclined plane in order to decide whether a certain mathematical definition of uniformly accelerated motion describes the acceleration which one meets in nature in the case of falling bodies. The persons in the dialogue seem to be satisfied with some mathematical reasoning which shows that the velocity increases with the units of time elapsed rather than with the intervals of space traversed. But when Simplicio asks for an experiment to show that the mathematical conclusion has physical reality in the sense of describing observable phenomena, Salviati replies that this request is a very reasonable one, for this is the custom, and properly so, in those sciences where mathematical demonstrations are applied to natural phenomena, and where the principles, once established by well-chosen experiments, become the foundations of the entire superstructure. Here, experiment does not confirm conclusions, it establishes principles, not by inductive generalization, but by comparing actual measurements with mathematical expectations. Without experiment, but not without inductions from experience. Without measurements, but not without recourse to observation. Aristotle's Physics, and with it such physical treatises as his works, on the heavens and on generation and corruption, represents a philosophy of nature in Aristotle's meaning of the term science. These treatises expound sciences, but they also constitute one part of philosophy, to be distinguished from mathematics and from what Aristotle regards as the first or highest part of philosophy, i.e., the science of metaphysics. Aristotle's tripartite division of the theoretic sciences, or speculative philosophy, into physics, mathematics, and metaphysics raises a question concerning his numerous biological works, and perhaps also his treatise on the soul. Are these to be classified as physical sciences, or parts of natural philosophy? The fact that Aristotle distinguishes between the forms and properties of living and non-living matter does not seem to affect the answer. By his criteria of physical inquiry, namely that it investigates what neither exists nor can be conceived apart from matter and motion, and that it is concerned with every type of change. All these works belong to the domain of physics. Accordingly, even such apparently psychological studies as those dealing with sensation, memory, dreams, justify a title under which they have been traditionally grouped, parva naturalia, i.e., short physical treatises. For all of these more specialized considerations of natural phenomena, the physics seems to serve as a general introduction as well as being in its own right an exposition of the most fundamental science. In the sphere of natural philosophy, it tries to define change and to state the principles underlying every type of change. It tries to classify the types of change, separating coming to be and passing away, simply, or generation and corruption, from coming to be in a special respect, or change in quality, quantity, and place, which Aristotle usually calls motion, in distinction from becoming or generation. It undertakes to analyze the conditions or causes of change or motion, to distinguish what happens by chance from what happens of necessity, to discriminate between natural and unnatural or violent motions, to treat the relation of mover and moved, to deal with the continuity and divisibility of motions, to consider place and time as conditions or aspects of motion, and to ask about the infinity of body and of change, and about the eternity of motion, or the whole order of becoming, the natural world of things in motion. Aristotle's physics thus seems to stand in sharp contrast to the physics of the experimentalists, not merely in method, but in the questions it tries to answer, and in the principles to which it appeals. The effort to define change in general and to state the principles and causes operative in every type of change might appear to correspond to the search for formulae of maximum generality to cover all natural phenomena. But where Newton and Fourier hope thereby to reduce nature's variety to the simplest terms, a few laws of motion, comprehending the whole framework of nature, Aristotle tends on the contrary to insist upon an irreducible variety of types of motion, kinds of matter, and causes of change. Furthermore, the principles to which Aristotle appeals are not mathematical. He criticizes the discussion of becoming, which takes place in Plato's Timaeus, on the ground that it tries to substitute mathematical for physical terms in the analysis of change. Physical bodies contain surfaces and volumes, lines and points, he writes, and these are the subject matter of mathematics. But the mathematician is not concerned with these things as the attributes of physical bodies, but only as separated in thought, at least, from matter and motion. There are sciences which represent mixtures of mathematics and physics, such as optics and harmonics, but the existence of these mixed sciences, the equivalent of what is later called mathematical physics, seems to Aristotle to imply, rather than deny, the separation of purely physical science from pure mathematics. Where Newton, who can be taken as the exemplary author of a physics which is at once mathematical and experimental, goes to mathematics for the principles of natural philosophy, Aristotle seems to think that physics has its own proper principles. If any deeper understanding of these principles is sought, it is not to be found in mathematics, but in metaphysics, or what Aristotle calls the first philosophy. For example, matter, form, and privation are proposed by Aristotle as the basic physical principles. In such terms, he is able to state his insight that all change involves a substratum for that which changes, and contraries, or that from which and that to which the change occurs. But the analysis of matter and form in terms of potentiality and actuality as modes of being, and the consideration of form and privation in terms of being and non-being, belong to metaphysics rather than physics. Furthermore, Aristotle, as a physicist, deals with bodies in motion and with the differences between the generation of bodies and their alteration, increase and decrease, or change of place. But he leaves to metaphysics, to the books which come after the books of physics, the discussion of physical bodies as substances composite of matter and form, and the distinction of substance and accident, which bears on the difference between substantial and accidental change, i.e., generation and corruption, as opposed to the change in quality, quantity, or place. Though for Aristotle physics is as separate from metaphysics as it is from mathematics in subject matter, physics depends upon metaphysics as it does not upon mathematics for the establishment as well as the elucidation of its principles. It is in this sense that metaphysics is logically prior to physics, but there may also be a sense in which philosophical physics is logically prior to experimental natural science. To the extent that the experimentalist employs physical as opposed to mathematical principles, he may have to derive these from a philosophy of nature. Galileo, for example, investigates the properties of natural and violent motions in the third and fourth day of his two new sciences, i.e., the motions of freely falling bodies and of projectiles. The problem of establishing the reality of this distinction and defining the natural and the non-natural types of motion seems to be a matter of philosophical analysis rather than of experimental investigation. Bacon and Kant appear to agree with Aristotle about the separation of physics from mathematics. Rational, or pure as opposed to empirical, physics is, according to Kant, entirely separate from mathematics. It is not to be confused with what is commonly called physica generalis, which is mathematics rather than a philosophy of nature, criticizing the natural philosophy of the ancients because it is corrupted by logic in the school of Aristotle and by mathematics in the school of Plato. Bacon says that mathematics should terminate natural philosophy rather than generate or create it. We may hope for better results, he adds, from pure and unmixed natural philosophy. Bacon, elsewhere, observes that the investigation of nature is best conducted when mathematics are applied to physics. He does not deny the great use of mathematics in physics, but rather insists that mathematics be regarded as an appendage or auxiliary of natural philosophy, not its master. He is writing against the mathematicians who would have their science preside over physics. But to whatever extent Aristotle, Bacon, and Kant are in agreement concerning the relation of physics and mathematics, their theories of the scope and subject matter of physics seem to be at variance. For Bacon, physics is only one of the theoretic parts of natural philosophy. The other is metaphysics. Both are sciences of nature or the physical world. The one investigates material and efficient, the other formal and final causes. Period. Both studies, moreover, can be conducted experimentally and can yield practical fruits in mechanics and what Bacon calls magic, through the production of effects by the application of a knowledge of causes. For Kant, the whole body of theoretical knowledge which is rational and a priori, not empirical and a posteriori, is the metaphysic of nature, of which one part is rational physics and the other rational psychology. The metaphysic of corporeal nature, he writes, is called physic, or because it must contain the principles of an a priori knowledge of nature, only rational physic. Here, physics and metaphysics do not have distinct objects as they do for Aristotle, nor does Kant's conception of physics as purely a priori knowledge of nature seem to agree with Aristotle's conception of physics as inductive and empirical, if not experimental. These issues concerning the relation of physics to mathematics and metaphysics have significance for the experimental as well as the philosophical study of nature. If, for example, following the position taken by Hume, metaphysical injury is dismissed as incapable of yielding knowledge, and mathematical knowledge is restricted to the realm of ideal entities, then natural science, which for Hume consists in experimental reasoning about matters of fact, becomes the only knowledge of reality. Even though Hume looks upon the conclusions of experimental reasoning as at best probable, it remains the case that questions about nature, which cannot be answered by physics, cannot be answered scientifically. The effect is the same as that achieved by Hobbes, who makes physics the primary science of reality on the ground that nothing exists except bodies in motion. The assertion of the primacy of physics, in short, may be due either to the denial that immaterial objects can be known by us, or to the denial that such objects have any real existence. Of quite opposite tenor is the view that only immaterial and eternal things can be scientifically known, and that the sensible world of things which come to be, pass away, and are forever undergoing change belong to the realm of probability and opinion, not knowledge. For Plato, mathematics and dialectic can be respectively science and wisdom because they study the intelligible reality of being in its immutable forms. But the physicists who try to give an account of becoming and all its changing, sensible appearances can do no better than adduce probabilities as likely as any others. On such matters, Timaeus says we ought to accept a tale which is probable and inquire no further. After discoursing at length of physical matters, Timaeus apologizes for the merely conjectural character of his account of natural phenomena, saying that a man may sometimes set aside meditations about eternal things, and for recreation turn to consider the truths of becoming, which are probable only. He will thus gain a pleasure not to be repented of, and secure for himself a wise and moderate pastime. This view goes further than Hume's in deprecating physics by contrasting its probability with the certitude of mathematics. It praises mathematics and dialectic, as Hume's theory does not, for something more than their certitude, for there being knowledge of reality rather than of appearances. Furthermore, Hume, unlike Plato, does not think the probability of physics detracts from its utility, the sort of utility which Bacon magnifies more eloquently than Hume. The invention of machines and the technical application of physics, whereby man extends his dominion over nature. In the traditional discussion of the dignity and value of physics, Plato and Bacon seem to represent attitudes as far apart as are the theories of Aristotle and Newton in the discussion of the subject matter and method of physics. I don't think I have much left in the category of science topics. Maybe just hypothesis. And I don't know if I did astronomy yet. But after that, I think all that's left is the more government-related topics. Coming down the home stretch. By the way, this series of introductions to the great ideas has got to be taken as just an entire work. One of the best educational overviews of knowledge ever written, if not the best, at least in English. The way it has been organized, categorized into 102 ideas, and backed up with all these cross-references and additional readings and citations. They really did a phenomenal job at consolidating our civilization's knowledge and the main sort of pioneers of it into, I guess, about 800 pages. I don't know how many thousands of words in modern English. I mean, I don't usually read a lot of educational content like this, but I'd imagine that this Syntopicon is a pretty special achievement in the educational realm. I mean, each introduction is written by somebody with a large level of expertise on what has been said about the topic in the literary tradition. So, as I predicted, my time has been extremely well spent reading all of these introductions. I knew it would be because of how good How to Read a Book is by Mortimer Adler. I haven't read some of his other books, but How to Read a Book is what he's best known for. And I remember reading that and being really impressed with his expertise. But it's interesting to think about kind of the topic of studying things like a scientist. Now you can and why that might be a useful ability to have in life. Because there's a lot of things that people do and that people have created that nobody's really studied completely yet, I would imagine. And if you can study something that nobody's written any books on yet, that is kind of like a significant phenomenon in your society, your world, gain like a special understanding of it that nobody else has at that time. You can sort of wield a special power over whatever it is. For example, I've been working on my trading card game rule book for years now in my free time, because it's just a topic that's really fascinated me. The topic of game design, turn-based game design. I guess specifically 1v1 collectible card game rules and mechanics. And nobody's like written any books on that I know of, on game design. But people are making board games nowadays like crazy. That industry is blowing up. And everybody's coming up with new ideas for games. So in my case, I've thought about turn-based card game rules and sort of the design aspects of these trading card games that people have come up with. I think to a degree that probably few people have. And I've been able to sort of quantify things. I mean, I'm sure people have thought more than me and better than me about turn-based games already, but nobody's like written anything about it, as far as I know. There's probably a lot of YouTube content about it. But I think it's an interesting field of study. All the different designs and mechanics people come up with. Because in a way, it's very similar to software development, which I spend so much time thinking about. Turn-based game design. It's something you could always easily recreate with software, which is what I think kind of makes it interesting. As opposed to like something that is a video game that has more rules in terms of physics or space and movement. Turn-based games, it's more like math and probabilities and different phases and like Boolean operations and or statements, if statements, then statements, do while loops. So I think while I've spent all this time thinking about software, pages of software troubleshooting bugs, trying to implement new features, refactoring code to clean it up and reduce duplication, ambiguity, and all that kind of stuff. Analyzing code. It's put my mind in a sort of mental space where I think about things like or it's sort of developed an instinct in me where I look at something, a game, for example, a card game, a board game, because I've always been interested in that kind of stuff. And I think about it in terms of what's sort of impure about it, what is clunky, what is a design flaw, what is not elegant about it mathematically or whatever. And naturally I want to fix that stuff. We'll look at Magic the Gathering or whatever, or Keyforge, or Flesh and Blood, or Hearthstone. Or some other board game. Chess. When you think about chess, it's like, okay, well, what is elegant about chess? Because there's not much wrong with chess, as far as I can see. Poker, Texas Hold'em is like a very pure game. That's why people love it. There's so much replayability. There's a purity aspect to it. What is it that makes a game fun? Fun to nerds, anyway. Nerds that like to think super deeply about the game they play and like compete against each other over and over and over their entire lives. Anyway, my point was just that even though I don't plan on ever doing any experimental science in my life, it's still kind of worthwhile to study how these guys thought. These pioneers of science. Because you can replicate that in your own life. Think your way out of where you are and to where you want to be. Mind is the master. That's another thing I've sort of, with all this book reading I've done the past couple of years, another thing I've sort of begun to realize is that human beings, or at least myself, with our minds compared to the other beasts on this planet. The animals. We've got these brains that are just have power beyond our own understanding. The way the mind works is like incomprehensible even to itself. Just intelligence is just a weird thing. Like you get ideas seemingly out of nowhere. And the more you feed your brain, the better it is at consuming. That's one thing I read or heard one time, is that the human brain never stops developing in complexity the older you get. I mean, obviously people's mental health deteriorates as they get older, but I think that's from, well, lack of cholesterol mainly. Cholesterol lowering drugs. But as far as the brain as an organ, if you're not poisoning it somehow or depriving it of nutrients, I guess just gets more and more complex until the day you die. It never like breaks down in its internal structure, whatever that is, the neuron network.